So lab exam 3 is this week. That's the last lab exam. Um, and it's cumulative, so it's everything that we've talked about in labs up to this point is on it. Um, Anybody have any questions about the lab test? The last one that the last lab period we had, I just went over lab exam 2. Yeah. Before that, the last new topic was a pretty simple idea. Um, that was the one that just said because of Newton's second law, that says F net is equal to the mass, which is a positive number, times the acceleration. Once you know the direction of the acceleration, that's also the direction of F net. So that's the new thing that came up in the last lab. Um, any other questions or kinds of problems you'd like to see an example of for the lab test? Okay. Um, so now we're moving on to a new topic. Uh, it's still pretty heavily related to Newton's second law, but um, now we're just going to be talking about circular motion. And there's some stuff that we know in circular motion that we don't know in other kinds. So, there's information we can use. Um, so circular motion. Um, so the idea of circular motion is something that we've been doing in labs for a long time. Uh, so if you have an object um, moving in a circular path, and let's say the object's here, and let's say it's going this way, and uh, let's say it's slowing down. Then the velocity vector would be like this. Since it's slowing down, the parallel part of the acceleration is like that. And it's turning this way, so the perpendicular part of the acceleration is like that. And then if we don't know anything about the magnitudes of um, a parallel and a perpendicular, then there's a range of possible directions. But in the class, we're always doing more calculations than just sort of this intuitive thinking about directions. So um, once you have the parallel and perpendicular parts of the acceleration, the total acceleration is equal to this plus this. Okay, so those aren't new ideas. So now I'm going to give you a list of the the three things really that are new with circular motion, with the calculations that we're going to do in class. Um, so there are only three new things. And two of those three things are just new names. Okay, so the first new thing is that Aparallel, if the motion is circular, so if something's moving in a circular path, aparallel is going to be called the tangential acceleration. And I'll write it as A tan. Well, why is it called the tangential acceleration? I mean, that would make sense in every case to call it parallel tangential acceleration because it's always remember. So um, it's just that if it's circular motion, we're going to call it that. And the second one, the second new thing is that perpendicular part of the acceleration has a new name. So A perpendicular is going to be called the centripetal acceleration. And I'm going to write that as A sin. And it's called that because if something's moving along a circular path, that perpendicular acceleration always points towards the center of the circle. So that's what centripetal, this word centripetal means, toward the center. Okay, so two of the three new things are just that we have to call old stuff new names. But here's the new thing that we didn't know before. The magnitude of the centripetal acceleration is the speed squared divided by the radius of the circle. So v here is the speed of the object. R is the radius of the circular path. Okay, that's totally new information. And you can see how that's really useful. If you know the speed that the object's moving and you know the size of the circle of the path that it's following, you can use this to calculate that perpendicular part of the acceleration, and then you can use that to calculate some other variable, you know. So let's think about a few things with this equation. So first of all, let's make sure that the units come out right. So if you're in SI units, what are the units of speed squared? What are the units of speed? Meters per second. So speed squared is meters squared per second squared. And then divide by what's the units of the radius of the circle? Meters. So you have meters squared per second squared divided by meters. That cancels one of the meters squared in the numerator, and you get meters per second squared. So the units work on that. And then second, think about being in a car doing donuts around a parking lot or something. Does this formula make intuitive sense? Okay, so say that you're, so say first that you're going around a big circle around the parking lot, okay? And you're gonna measure the centripetal acceleration by how sick to your stomach you feel as you go through this turn, okay? So first, you're in a big circle going 20 miles per hour. That's your default. You can feel the acceleration, you know, like, and it's also the reason that you keep bumping into the person next to you, you know, is because the car is forcing you to accelerate. So now you started at 20 meters per second. Now you go around the same circle at 30 meters per second. 40, that's 30 meters per second. So you go faster. If you follow that same curve, that same circular path at a faster speed, do you feel more acceleration or less acceleration? More, and that is indicated here. I mean, if you, that's in the numerator. So 20 squared is 40. 30 squared is, no, 20 squared is 400. 30 squared is 900. So you have a bigger acceleration if the radius of the circle is the same and you go faster around the circle. Okay. Yes. We will. Yeah. But right now we're just thinking about the magnitude. I mean, think about, so we already know the direction of that perpendicular, the centripetal acceleration. It's toward the center, you know? And so we know the direction, and now we have a way to calculate the magnitude. And so if you combine those two, you have the full vector, and you can do calculations. Okay, so now let's think about, the fact that the speed is in the numerator, that makes sense. What about the fact that the radius of the circle is in the denominator? Does that make sense? So now think about, the first thing we did was go 20 meters per second around that original big circle, okay? And now we make the circle half as big. So now you're still going 20 meters per second, but you're doing it around a lot tighter circle. Does that make you accelerate more or less? More. So we made the radius smaller, and the effect was making the acceleration greater. If you go in a wider circle, you know, you could go in a circle so wide that your body doesn't even notice that you're not in a straight line, you know, then the acceleration's really low if you have a huge R. If you have a tiny R, if you're forcing yourself to turn really fast, the acceleration is big. So you can make intuitive sense out of this equation. There's no, like, you can't really make intuitive sense out of whether this is squared or not, or whether there's a constant. But you do know that increasing speed should increase the centripetal acceleration, and increasing the radius of the circle should decrease the acceleration, and that's what we have here. Okay, so that is thing that's new. That's the end of the new stuff. So circular motion, like when we talk about acceleration in lab, you know, there's some cases where the object isn't changing speed and all it's doing is turning. And there's some cases where it's doing both. And then there's some cases where it isn't turning, it's only changing speed. If it's moving in a circle, it's always turning, right? So that possibility isn't available. So the only possibilities are that it's moving in a circle without changing speed, or that it's moving in a circle while it changes speed. And so, okay, so remember that the acceleration vector has to be the sum of the tangential acceleration and the centripetal acceleration. Centripetal acceleration is the one that always has a magnitude of v squared over r. And so there are only two possibilities. The first one is that the speed is constant. In that case, the total acceleration is just equal to the centripetal acceleration because the tangential is 0. And this is called uniform acceleration. And the only other possibility is that the speed is changing. Then the total acceleration, you have to add these two parts together, the tangential and the centripetal. And that's called non-uniform acceleration. So I'm going to give a general set of steps for problems, everything except one type of problem that it's going to have sort of its own method because it's a lot easier to do it another way. And then we'll just do a few example problems. So here's a general set of steps for circular motion problems. Except what I'm going to call tetherball type problems. So we'll get to those after. Okay, is it a coincidence that one of the types of circular motion is called uniform circular motion, and that this is a general set of steps, and generals wear uniforms? Yes, that's totally unrelated. Okay. Okay, so the first step is choose a view where the circular path appears as a circle. You can see the circular shape. And when I say a view, what we're really doing is choosing where our coordinate system lies. How, like, does our coordinate system tilt up like this or lie flat, you know? But so we're choosing a view where the circular path is visible as a circle. Visible as a circle. Okay, so here's an example. So say that you're doing a problem with a toy train, because I'm really good at drawing this train shape. Okay, and this train goes around a circular path like this. So when you're going to do a problem like this, even if the problem shows you a picture like this from the side, this view doesn't show the path as a circle. You know what I mean? So what you want is either view from above looking down or a view from above, you know, from underneath looking up, where the view that you see is a circle. Okay. And so the view that we would want in that case would be, you know, like the top down view where you see like something like this. This is the one we want. And like I said, what that really means mathematically, because the way you're looking at a problem doesn't have any mathematical, you know, impact on the problem. But what that really means is that your coordinate system is in that plane. Okay. And so all your vectors are going to be defined in that coordinate system. Then the second step is to choose a point on the path that you're going to analyze. So like, for example, in the problem that I drew up above, this toy train, so there's the coordinate system. And, you know, in some problems, it tells you a specific spot on the circle that you should think about. In other ones, you just have to choose one and just be consistent with it for the rest of the problem. So let's say we're going to think about the train at this location here. Step 3, draw a vector from that chosen point toward the center of the circle. Give it the magnitude v squared over r. Then this is the centripetal acceleration. So in the example that I've been using, so here's the coordinate system. Here's the point we're looking at. Now draw a vector from the point we're looking at toward the center. That has a magnitude of v squared over r. Sometimes in some problems you already know what r is, or maybe what v and r both are, and then you can fill that in with a number. Sometimes you just have to leave one or both of them as variables. And notice that the way I have this drawn here, so in this example, we can write this as vector components. So the centripetal acceleration vector, that arrow's pointing in the negative x direction. You see that? and it has a magnitude of v squared over r, so we can write this as negative v squared over r for our x component, and then 0 for our y component. Um, 4. Now, this is only if it's non-uniform circular motion. So if you're dealing with non-uniform circular motion, remember what non-uniform circular motion is? Yeah, if it's speeding up or slowing down. So this step has to do with the tangential acceleration, and it doesn't exist. You don't have to worry about it if the speed's constant, but you do have to worry about it if the speed's changing. So then draw the tangential acceleration based on whether the object is speeding up or slowing down. Okay, so in the toy train example, that's the location we care about. Here is the, let's see, here's the centripetal acceleration. It has a magnitude of v squared over r. And now I didn't say whether it was speeding up or slowing, which one it was, but let's say that it's slowing down. Then the velocity would be like this. And that means that what we're used to calling the parallel part of the acceleration, now it's the tangential acceleration, would have to be opposite the velocity vector. I'll call that the tangential acceleration. And then step 5, the total acceleration is the tangential plus the centripetal. And now the last thing that you have to do in most problems is 6, draw a free body diagram. And then the last thing is you're going to use Newton's second law to calculate some kind of unknowns. So Newton's second law. One thing to notice with the free body diagram, so this will happen sometimes that, and this hasn't happened in any topic yet, but sometimes weight and or normal forces will be out of plane of the chosen coordinate system. An example of this is this train example that I've been doing. So look at it from the side and imagine a free body diagram of the train. weight force is going down there. The normal force would be pushing up. Okay. But this isn't the view that we're taking to do the calculation. We're taking this view here. So what does the weight and normal forces look like in this view? The weight is into the page. The normal force is out of the page. And so how do you deal with those as vectors? Well, when that happens in this class, you can just leave those out. Okay, you can just ignore them. Because we're going to be, and the reason you can ignore them, by the way, is because remember that the second common misconceptions had to do with the fact that the forces and accelerations and everything going on, say, along the x-axis, had no effect on the accelerations and forces on the y-axis. And that's also true, like in 3 dimensions. If we were going to do this in 3D, we'd have to have a z-axis coming out. Well, what's happening in the z direction doesn't have any effect on these, so we can just pay attention to x and y and forget about the stuff going on in z. And that's what we're going to do. So you can just ignore those. It sounds surprising, but you can. Okay. So let's just go through a few example problems. You know, I'll try to carefully go through these steps in order so you can sort of see how it works. So the first one, so let's say that there is a plane that's following a circular path. So here's the plane. Sort of looks like a dolphin, but and it's going through a circular path like that. Because it doesn't have a cockpit. Okay, and let's say that it's going through it's following a circular path. Here's the center of the circular path. And the radius of this circular path, I guess this isn't drawn to scale. Let's say the radius is 250 meters. And as it goes through this part of the circular path, it has a constant speed of 120 meters per second. And we want to know, what do we want to know? So first, what's the acceleration of the pilot at that, let's call that red point P. Well, the acceleration of everything in the plane is going to be the same, but this is the kind of calculation that needs to be done in certain maneuvers, and where you're for all sorts of reasons, because people can't withstand over a certain acceleration, or they can't withstand certain acceleration for longer than 5 seconds or whatever. So you have to know what kind of accelerations are going to people are going to have to deal with. So first, we're going to figure out just at that specific point, what's the acceleration of the pilot. And then we want to know, second, what's the force vector applied to the pilot by the seat at this point P? Why would we want to calculate that? Well, most likely it wouldn't be so important to figure out the force that the seat applied to the pilot, but we would calculate this so that then we could figure out, using Newton's third law, the force vector the pilot applies to the seat. And that's a more probably important question. I can't think of a reason why B would be very useful on its own, unless I suppose if you were nervous about like injury or something. But I think if you got to that point, you'd have bigger problems. But why would you want to figure out the force vector the pilot applies to the seat? Well, for example, like as you're doing the engineering of designing the cockpit, that's the kind of calculation you'd want to do to make sure that you were building your seat strongly enough that it's not going to break under the kind of forces you're applying to it. So these are pretty reasonable engineering questions to ask as you're thinking about the use of this plane. All right. So what's the first step? This is a circular motion problem. It's the first step. Yeah, so first we have to choose the view. And the way I've drawn this, we're already looking at the circular path. So I'll draw it as a full circle. And so our coordinate system is going to be like this. And by the way, it doesn't even matter if I sort of drew it as if this is going to be a constant speed over this whole circle. But if we're just trying to figure out the forces at that instant, really all we need to know is that it's not changing, that it's following a tiny part of a circular path without changing speed at that location. We don't care for this calculation that it's been on this constant circular path all the way from the bottom or anything. That doesn't matter. Okay, so there's step one. What's step two? Yeah, choose the point to analyze. So this is a case where it's chosen for us. You don't have to draw this all in separate pictures, but I'm just doing it so you can see the order of steps. So in this one, it said this has to be the point, like this is what we were asked for specifically, so there's no thinking there. 3. Yep. So is x, y. There's the point. So that means the centripetal acceleration is pointed this way. In this case, it's in the negative x direction. and v squared over r. This is a case where we know both of these. So that's 120 squared divided by 250. And that's 57.6. So we already know what the centripetal acceleration is. It has a magnitude of 57.6. It's pointing in the negative x direction, so this is going to be negative 57.60. It's in SI units, so that would be in meters per second squared. Any questions about any of these yet? Okay, what's step 4? We don't need it. That's right, because this is uniform circular motion. Uniform circular motion. So the tangential acceleration is 0. And so then what's step 5? Yep, so A total is equal to the centripetal, which is negative 57.60, plus this is the 0, 0 here is the tangential. You know, that's a tangential. This is a centripetal. And so the total acceleration vector is negative 57.60 in units of meters per second squared. And by the way, this is what the question asked for part A. So that's the answer. The acceleration vector for the pilot is negative 57.60, or if you just want a magnitude for the acceleration, it's 57.6 meters per second squared. Is that survivable? Anybody have an idea? Anyone? It is actually, yes. It's very high, but so for short periods of time. Okay, so there's two things that are like, to not be survivable by itself, you'd have to have a huge acceleration, like to cause bleeding or something. But for a pilot, something that makes you pass out is also not very good for you. You know what I mean? So that's really the problem, is like not what'll burst blood vessels or something, but like what someone can stay conscious through, you know. But yeah, so when somebody says, like, a pilot talks about, you know, 4Gs or 7Gs or whatever, they're talking about how many times the acceleration of gravity they're, you know, enduring. So in this case, if the acceleration of gravity is like 9.8, this is a little less than 6 Gs, which is a very big acceleration. But people who know what to do to stay conscious, like apparently there's, like, they do exercises and stuff, like practice dealing with it. For a short amount of time, they'll be okay for that. You wouldn't want to go through a multiple second thing like that. Everything I know about this is based on uh, a Nova episode I saw when I was like 8. I watched like 4 minutes of it before I realized Love Boat was on channel 11 or something. Okay, so that's part A. Now we want to calculate the force that the seat applies to the pilot. And that goes along with um, step 6. Step 6 and 7 is draw a free body diagram of the thing you want to calculate the forces on and use Newton's second law. So free body diagram of the pilot at this instant. So when the plane is at the point P, the airplane is going straight up into the air at that instant. And so an outline of the pilot would, the pilot would be looking straight up into the air. So it would be like, sitting like this. Oh, I didn't give his math. Let's pretend I did. So let's say the pilot's mass is, what do I have here? 100 kilograms. Okay, so in the view that we have, the coordinate system that we're using, does the weight appear or is it out of the plane? It's in the plane and acting just straight down like this. And the magnitude is 100 times 9.81, so 981 newtons. And then the force applied by the chair, let's think of that in two separate parts. There's going to be, the back of the chair is going to be pushing this way. And the top of the chair, the seat of the chair is going to be pushing this way. And then is anything else touching the pilot? We'll just lump the steering, like, I hope he's also holding some kind of steering wheel, but we'll just lump that in with that's probably small compared to the seat forces. So then that's good. And so now we can go to Newton's second law. Let's see. Okay, so now let's put this all together. So there's the free body diagram. We have a downward force, 0, negative 981. The force from the top of the chair is in the negative x direction, so that's negative F top 0. The force from the back of the chair that's in the positive y direction, so that's 0 F back. And that's equal to the mass times the acceleration. The mass is 100. What do we know about the acceleration? Yeah, that's what we just calculated. So negative 57.60. And what we're trying to calculate is, like, if we add up these two vectors together, that's force vector on the pilot by the seat. We just have to figure out what those two variable values are. So the x equation says negative F top is equal to negative 5,760. So F top is equal to positive 5760. And the y equation says negative 981 plus 0 plus F back is equal to 0. So F back is equal to positive 981. And now we can plug these into the force vectors. So the force on the pilot by the seat is negative 5760, positive 981. I just added those two vectors together to make one. And the units are newtons. That's the force on the pilot by the seat. So Newton's third law says the force on the seat by the pilot is, just take opposite sign for each one of the components. So positive 5760, negative 981. And then you can decide how thick the steel beams need to be, or whether wicker is okay, that kind of thing. They don't really use wicker. Maybe they do. I've never been in there. Yep. The back of the chair on the back. Any questions about that one? Okay. Let me do another one. Okay, so let's say that there's there's a little ball that's connected to a cable. Let's see. Okay, so this ball is connected to a cable. And it's traveling in a circular path around a little post. And let's say that, so there are two things going on. It's attached to that string that's keeping it rolling in a circular path. And it's also rolling along like a glass, low friction surface. We're going to ignore any friction. So we'll say that it's going this way with a constant speed of 6 meters per second. And let's say that the ball has a mass of 0.06 kilograms. And we want to calculate the tension in the string. So again, this could be like, if that's part of some kind of, I don't know what kind of machine would have something like this going on, but if that's something that you have a device that needs to have this part doing this thing, then we need to know how strong that cable, that string needs to be. And we can do that by calculating what the tension is going to be and then choosing the thickness of the string based on that. It's not, that's a good question. it's very close to being a tetherball problem, but the difference here is that the surface is there. So if that surface wasn't there and it was spinning around the string without anything supporting it from underneath, then we would use a different method. Okay, so this time I'm not going to write out all the steps. I'm just going to go through them, but I'm going to draw it on a single figure. Okay, so what view do we want to take? Yeah, top down. Um, so there's the circular path, and here's the coordinate system. And in this problem, it doesn't say anything about where on the circle we're supposed to do this calculation. So we get to choose, and the answer would be the same no matter where. So this time I'm going to choose down here. I would definitely, when it's up to you to choose, I would always choose one of these four spots here, here, or here, or here. Any other ones, you can still do the problem, but you'd have to use cosine and sine of phi angles, and it's just unnecessarily complicated. So choose one of those four spots. Um, now draw a vector that goes from the point you care about towards the center. That's the centripetal acceleration. And the magnitude of that acceleration is v squared over r. And I didn't give the radius, I'll bet. I'm stupid. But I bet it's in my notes. Let's say the radius of the circle is 5 meters. Okay, so v squared over r is speed is 6 meters per second, so 6 squared divided by 0.25. That's 36 times 4, 144 meters per second squared. And then in this case, centripetal acceleration, you can see it's in the positive y direction. So this is 0, positive 144. Anybody have any questions about that? And now what about the tangential acceleration? There isn't any because this is constant speed. So it's uniform circular motion. And that means that the total acceleration is 0, 144 plus 0. So 0, 144. And now we have the total acceleration. Now we're going to draw a free body diagram of the ball. Um, well, we're looking at the ball in this view from above when the ball is at the, at the bottom of that circle. So here's the ball. And so now let's think of all the forces that are acting. Um, there is a weight force. Which direction does that go? You got to be careful on this. So this is one of those cases where things are happening that aren't going to show up in our coordinate system. So if we have a top view um, from above looking down, the weight force is going into the page. So we can just leave that off. Then there's also a normal force uh, that's the glass pushing up on the ball, but that force is coming towards us. So that doesn't show up. So the only force that shows up is the cable force, T. By the way, another way, a way that some people indicate this stuff, if you don't like just leaving that completely off, you can represent forces going into the page as, so think of um, the weight force going into the page, you represent um, as a circle with an X in it. And you can think of that as like the feathers of an arrow. It's like you're seeing the arrow go away from you. Um, this is a standard way that people represent that. And then the normal force, that's a vector where you'd see the point coming right to you. So you represent that with a little dot, like you're looking at the tip of the arrow. And that would be N. And then you have the cable force like this. And I don't care which one of those you do, but if you like putting all of those forces in there, then that's how you would represent it. And then the last step is Newton's second law. Um, so Newton's second law says 0t, that t is in the positive y direction, is equal to the mass of the ball times its acceleration um, the x equation doesn't give anything useful, but the y equation says t is equal to 0.06 times 144 or 8.64 newtons. So you would need to do this, you would need a string that can withstand a force of 8.64 newtons, like 2 pounds of force. Yes. No, we didn't put any friction in. Yeah. But you're right. If it was friction, that would be another force you would have to put in there. Okay, let's do one more. Okay, so let's say there's a kid on one of those, the carousels that they don't put in playgrounds anymore because of all the fatalities, probably. But there are little handles on it, and you sit on the edge, and then a bigger kid comes and pushes it until you cry. You know what I'm talking about? So I know Lydia, what I'm talking about. Oh, you probably don't have one at your at your school. because they're too dangerous. Okay, well, the kid sits here like this. And sits on the flat part of the carousel. And then there's like um, these things to hold on to, but they don't help as much as you would think. And it's going this way. Okay, so the big kid like grabs onto these and pushes it and spins it around. You know what I mean? Okay, so let's say that the kid has a mass of 15 kilograms. And let's say that the radius of the carousel is 2 meters. And let's say that at the instant that we're looking at, so at this chosen instant, the kid's speed is 4 meters per second, and the kid is speeding up at a rate of, let's say, 6 meters per second squared. Um, so let's calculate the acceleration. What's the kid's acceleration vector? Okay, well, first we have to choose a view. And so I'm going to choose a top-down view. And we have to choose a point on that circular path to deal with. Let me draw the coordinate system. And it doesn't matter which one of these 4 points you choose, but I'm going to choose a different one again, just, so you can sort of compare those. So let's choose that point over there. Okay, then the centripetal acceleration vector goes this way. And v squared is 4 squared, so 16. Radius is 2 meters, so 16 over 2 is 8 meters per second squared. And so the centripetal acceleration vector is 8, 0. Any questions about that? Okay, now we have to think about the tangential acceleration. We haven't had that in either of the two examples so far, but this time he's speeding up, so we know we're going to have tangential acceleration. The velocity is like this. He's speeding up. So which way is the tangential acceleration? Up or down? Yep, down. It has to match the velocity direction. And we're given the magnitude, speeding up at a rate of 6 meters per second squared. So this is going to be 6 meters per second squared. That's in our negative y direction. So the tangential acceleration is 0, -6. The total acceleration then is just the sum of those two pieces. So 8, 0 plus 0, -6. And so 8, -6 meters per second squared. And then this didn't ask anything about forces, but the next part of the question could be like, what horizontal force is required for this kid to stay in that circular motion? And then we could use Newton's second law to calculate that. Any questions about that? Yeah. Yeah, that's a good question. I mean, I guess we haven't really done anything exactly like that, so I guess I would have to give more details. But actually, that's the right way to think about it. Yeah, um, you'd have a weight force and a normal force, and then you'd have, well, maybe the question would say something about where those forces are coming from. Maybe there's one that's coming from holding on to the handle. Maybe there's one that's coming from friction, most likely. And so, but I'd have to say more about it. Any other questions? Okay, that's all.